So we're moving into chapter 17. I'm actually skipping to the last part of chapter 17, which is on solubility equilibria. So we've looked at various specialized versions of Kc in the last couple chapters. We're in chapter 17 now, as I said. And so Ksp is what's called the solubility product, and that's a form of Kc that governs the solubility of sparingly soluble compounds. And so when I say that, what I'm talking about is when we were back in chapter 4 and we talked about certain ionic compounds, we spent more time talking about compounds that are soluble in water. But there are a lot of ionic compounds that are not soluble in water, except that they are soluble to a small extent. Everything is soluble in water to a certain extent, and it's governed by an equilibrium constant. And so this is called Ksp. Remember that we don't include solids in a K expression, and so since in any solubility equilibrium the reactant is a solid, there is no denominator, and so that's why it's called Ksp. It stands for solubility product. And so, for example, if we have a classic example of a sparingly soluble ionic compound is silver chloride, and so it will dissolve a little bit. It is governed by an equilibrium constant expression that looks like this. So it's the product, it's the concentrations of the products raised to the power of their coefficients. And because the reactant is a solid, there's no denominator. And for silver chloride, that value happens to be 1.8 times 10 to the minus 10. So you can see that silver chloride is not particularly soluble in water. We could take another example, barium sulfate. Barium sulfate is another compound that is often made as a precipitate in various lab experiments and stuff like that. Once again, it's going to be, because the coefficient of the barium and the sulfate, those coefficients are both 1, it's just going to be the concentration of the barium times the concentration of the sulfate. And for that reaction, the value of Ksp is equal to 1.1 times 10 to the minus 10. It's just kind of coincidental that that the first two we looked at have similar solubilities. So that's the concept of the solubility expression, the Ksp expression. It's going to only include the products because the reactant is a solid, so it's not going to have a denominator. It's going to be the concentrations of these product ions raised to the power of their coefficients. And so here's an example of how these would actually appear. So this is Appendix D3 from the back of your book, and you can see for various relatively insoluble compounds, it gives the name. This is only just a little piece of the table that I've taken a picture of here. It gives the name, it gives the formula, and then it gives the value for Ksp. And you can see that they range from, on the low end, here 2.4 times 10 to the minus 5th, down to things like 1.6 times 10 to the minus 30th. So there's a wide range of Ksp values. Ksp is not the same as solubility, and we're going to talk about solubility in just a second. Ksp is an equilibrium constant. Solubility, we're either going to express the solubility of a compound in terms of molarity, that is moles of compound that dissolve per liter of solution, or as generally grams per liter. So you could have grams per 100 mils, but generally we're going to think about this either in terms of moles per liter or grams per liter. And so we can use Ksp to determine the molar solubility, and then we can multiply that by the molar mass to give the grams per liter solubility. So let's take an example of this. I'm going to start with a fairly straightforward example, which is the silver chloride example. Calculate the solubility of silver chloride in water, both in terms of molarity, moles per liter, and in terms of mass per unit volume, grams per liter. And so the first thing we do is write the equilibrium reaction. Solid silver chloride in water is going to partially dissolve to give you some silver ions and some chloride ions. And so we can set up an ice table for this. We don't concern ourselves with concentrations of a solid, and so I've just put a dash in there, which means we're not concerning ourselves with that. And in the beginning, before anything dissolves, I've got no concentration of the product ions. The change is going to be minus x for the silver chloride, plus X for the silver, plus X for the chloride. Why am I putting this in there if we don't care about the silver chloride? Because we want to know what the molar solubility of silver chloride is. So that X, even though it's not figuring into the equilibrium constant expression, is the amount of silver chloride that goes into a mole of water to make the solution. And so at equilibrium, we have X represents both the concentration of silver ions and chloride ions. And so from this equilibrium reaction, we can write that equilibrium constant expression for silver chloride. Ksp is equal to the concentration of silver times the concentration of chloride. And we said that that was equal to 1.8 times 10 to the minus 10. If I jump back here just a second, you'll see that those equilibrium concentrations are both X, both for silver and for chloride. And so therefore, Ksp is equal to X squared. 1.8 times 10 to the minus 10 is equal to X squared. And therefore, X is equal to the square root of Ksp, or 1.3 times 10 to the minus fifth molar. So that would be the solubility of silver chloride in terms of moles per liter. 1.3 times 10 to the minus fifth molar is a saturated solution at 25 degrees Celsius. We can also calculate that in terms of grams per liter. So we just had 1.3 times 10 to the minus fifth moles per liter. So if we put that onto the train tracks, 1.3 times 10 to the minus fifth moles per liter, and then we multiply that by the molar mass of silver chloride, which is 143.3 grams per mole. We get the solubility in terms of grams, which is 1.9 times 10 to the minus third grams per liter. So about 2 milligrams of silver chloride will dissolve in a liter of water. That was a very simple problem in which the molar solubility is simply equal to the square root of Ksp. But if we take something that has a more complex formula, that has more than 2 ions in its formula unit, it's gonna work differently. So let's take a look at cadmium hydroxide. If you go and look at the table that I showed the picture of earlier, you'll see that the Ksp for cadmium hydroxide is equal to 2.5 times 10 to the minus 14. So once again, we're going to write that equilibrium constant. We're going to write that equilibrium reaction. The key difference here is because the formula is different. There are 2 hydroxides in the formula unit. That means I'm going to have 1 mole of cadmium hydroxide will give me 1 mole of cadmium, but it gives me 2 moles of hydroxide when it dissolves. And that's going to affect our calculation in 2 ways. First of all, when we look at the ice table, you'll see that while the change in the cadmium hydroxide is minus X and the change in the cadmium is plus X because it's got a coefficient of 1, the change in the hydroxide is going to be 2X because there's a coefficient of 2 on the hydroxide. And therefore, at equilibrium, for every X moles of cadmium hydroxide that dissolve, I get X moles of cadmium ions, but 2X moles of hydroxide ions. The other thing is that because this has a 2 in front of it, the equilibrium constant expression has the hydroxide raised to the second power. And so Ksp is not just equal to cadmium times hydroxide, it's equal to cadmium times hydroxide squared. And so now if you go back, the cadmium was X, but the hydroxide was 2X. And so when we substitute those values into the equilibrium constant expression, X takes the place of the cadmium, but 2X takes the place of the hydroxide, and it's squared. And therefore, the Ksp value of 2.5 times 10 to the minus 14, whereas for a silver chloride, Ksp was simply equal to X squared. Now for cadmium hydroxide, Ksp is actually equal to 4X cubed. When I solve that for X, I get that X is equal to 1.8 times 10 to the minus fifth molar. Now this brings up an interesting little point, and I want to delve into this just a little bit. I'm sorry, before I do that, let me just say that we're now going to calculate that in terms of grams per liter. So we know the molar solubility of cadmium hydroxide. It's 1.8 times 10 to the minus fifth moles per liter. Now we can multiply that by the molar mass of cadmium hydroxide, which is 146.4 grams per mole. And we get 2.6 times 10 to the minus third grams per liter. So about 2.5 milligrams of this compound will dissolve in a liter of water. All right, now here's the comparison I wanted to make. For cadmium hydroxide, Ksp was on the order of 10 to the minus 14th, but the molar solubility was 1.8 times 10 to the minus fifth. For silver chloride, the Ksp value is actually much larger. This is like almost close to 10,000 times greater than this. And yet the molar solubility of these two compounds is very, very similar, 1.8 times 10 to the minus fifth, 1.3 times 10 to the minus fifth. How is it that their KSPs differ by almost 10,000, but their solubilities are nearly identical? That's because they don't have the same number of ions in their formula unit. Cadmium hydroxide has more ions, 3 ions in its formula unit, whereas silver chloride has only 2. And so what that means is you cannot compare, for these two compounds, you can't really look at their KSPs and say, oh, this one is just way more soluble than that one because its KSP is 10,000 times more. It turns out that they're very similar. So the question then arises, under what circumstances can you use KSP to compare the solubilities of two ionic compounds, just to qualitatively compare their solubility? And the answer is you can qualitatively compare solubilities for compounds that have the same number of ions in their formula units. And so I've highlighted a couple instances here. So for example, barium carbonate has 2 ions in its formula unit, 1 barium and 1 carbonate. Calcium sulfate has 2 ions in its formula unit, 1 calcium and 1 sulfate. And therefore, you can use KSPs in this instance to qualitatively compare solubility. So because calcium sulfate has a KSP which is 4 orders of magnitude higher than barium carbonate, you can say that with certainty that calcium sulfate has a higher solubility in water than barium carbonate does. They both have the same number of ions in their formula unit. Calcium sulfate KSP is a much larger number, therefore it's going to be more soluble. By the same token, I can compare cadmium hydroxide, which we just did, with calcium fluoride, because these both have 3 ions in their formula unit, 1 cadmium and 2 hydroxides, 1 calcium and 2 fluorides. Therefore, they are comparable to each other, and you can look at these two and say, oh, because calcium fluoride, the value of its KSP is about 1,000 times that of cadmium hydroxide, that this is going to be a qualitatively more soluble compound. What we can't do is compare calcium fluoride to calcium sulfate or compare calcium fluoride to barium carbonate. Because what you would actually find, I'm not going to do the calculation here, what you would actually find is that for calcium fluoride, although it has a smaller KSP than barium carbonate, its molar solubility is actually higher. But because this has 3 ions in its formula and this one only has 2, that makes the KSP value smaller. If this is confusing to you, you're always welcome to ask me about it, and we can probably spend some time talking about it in class. Let's just finish up by talking about some factors that will affect the solubility of compounds. One is what's called the common ion effect, and that simply means that if you have a product ion already in solution, so if you've got an equation like this in which you're trying to get barium sulfate to dissolve in water, and one of these 2 ions is already in solution, that's going to suppress the solution of this compound. Because if you think about this in terms of Le Chatelier's principle, if there's already a product present, that's going to tend to shift the equilibrium back toward reactants. And so an example of this would be to say barium sulfate is going to be much less soluble, has a much lower solubility in a solution of sodium sulfate than it would have in pure water because there is already sulfate present. Remember, sulfate's part of the equilibrium constant expression. whether it got there from the barium sulfate or from the sodium sulfate that was already there. So if I've already got some really high level of sulfate in solution, this equilibrium is going to be suppressed. It's not going to go as far toward products. Whereas if I put this into pure water, where none of these ions are already there, more of it will dissolve. So that's what's called the common ion effect, and we'll see this later when we talk about buffers and things like that. But if you have a compound in solution already, another compound in solution that has one of the same ions as the compound we're concerned with, that's going to decrease or suppress the solubility of that compound. Another thing would be pH. So if I have a sparingly soluble salt in which the anion is basic, then that's going to be more soluble in an acidic solution, and I'll show you down below in just a second why that is. And substances with acidic cations are going to be more soluble in basic solutions. But let's look at an example of substances in which you have a basic anion. And let's compare lead fluoride to lead iodide. So lead fluoride is not very soluble in water. When you put lead fluoride into water, just a little bit of it dissolves, and it gives you lead ions and fluoride ions. But if you add some strong acid to this, remember fluoride is a weak base, and that strong acid will react with the fluoride to form hydrofluoric acid. The result of that is now you are removing fluoride ions, that is product ions of the ionization of the solution. You're removing some of the product from the reaction by converting it into HF. That will cause more of the lead fluoride to go into solution. So they're trying to demonstrate this pictorially here. Here you're at equilibrium, tiny amount of lead fluoride has gone into solution. But now when you add H+, it effectively removes these fluoride ions from solution, and therefore you're removing a product that's going to drive the equilibrium forward. More lead fluoride is going to go into solution to try and replace those fluoride ions that are being reacted away by the H+. By contrast, iodide, because it's the conjugate base of a strong acid, is not a base, or it's a negligible base. And therefore, when I put H+ into a lead iodide solution, nothing's going to happen, because those protons will not react with the iodide, will not remove those iodides from solution, and therefore will not drive the reaction forward. The last thing we want to talk about is complex ions, and we've already seen this. We've already seen some examples of complex ions in the lab experiment we did on equilibrium. A couple of the ones that we saw in that instance were the iron 3 thiocyanate complex and the cobalt 2 tetrachloride complex. Neither of those two is listed here, but the formation of complex ions is very characteristic of transition metals. And so silver, for example, will form a complex with ammonia, and the K for that is fairly large. It will form a complex with cyanide, and the K for that you can see is even quite a bit larger. It will also form a complex with thiosulfate, and et cetera, et cetera. Various transition metal cations will form these complexes with bases, and some of these have K values that are very, very large. These are very, very thermodynamically favorable reactions. So what happens? We were talking earlier about the fact that silver chloride is not very soluble in water, and it's not. If I put some silver chloride into water, it'll just sit on the bottom, but just a little bit of it will dissolve to produce some silver ions and some chloride ions. Now, if I add some ammonia to that, remember this is a reaction that's favored at equilibrium. It's got a large equilibrium constant of 17 million. What that's going to have the effect of doing is forming the silver ammonia complex with any silver ions that are present. In order to compensate for that, more of the silver chloride is going to go into solution, because the silver ions keep being taken out of, you're essentially removing product, right? It's silver chloride going to silver plus chloride, but now those silver ions are reacting with ammonia to form the silver ammonia complex. And so that shifts that whole equilibrium to the right. And therefore, essentially, silver chloride is quite soluble in an aqueous solution of ammonia because all of the silver gets converted into the silver ammonia complex. And so the silver chloride just keeps dissolving to try and because it keeps shifting it toward the right. All right, I think that's the end. That is the end. Thanks for watching.